Hello everyone, welcome to today's tutorial. And today's topic is reduction. And the first example is Hamiltonian cycle and Hamiltonian path. Let's first review the definition of HC and HP. A Hamiltonian cycle is a cycle that visits each vertex in the graph exactly once. And the Hamiltonian path is a path that visit all the vertex exactly once. So the only difference is a cycle and a path. Okay, so next, let's see how we can reduce between HP and HC. So let's first see how to reduce HC to HP. Okay, so you have to go back to the starting point. So an example is, yeah, you have to visit because it's a cycle, so it looks like this. So you can, so you have like, you can visit the starting point more than once. Yeah. Okay. So suppose you have a graph G and you want to know whether it has a Hamiltonian cycle or not. And so this is a HC problem, and we want to reduce this problem to HP problem. Then we can randomly pick a vertex inside G, V, and we duplicate this vertex and create a vertex V prime. And because this is a duplicate vertex, so we will connect V prime to all the neighbors of V. So we will connect this, also this. And then we will also create two more vertices, V prime, U prime, and U. And we connect U with V and V prime with U prime with V prime. And so this new graph, let's call it G prime. So this is the created G graph for the HP problem. And the next, what we need to prove is that if G has a Hamiltonian cycle, then G prime will have a Hamiltonian path, and also vice versa. So let's first see this direction from G. If G has a HC, then G prime will have a HP. So if G has a HC, which means it's a cycle, and this is the node V, and we just need to suppose it connects to these two nodes. Yes, you're right. Finding a path is easier than finding a cycle because you can just, so for the same graph, if you find a cycle, you just need to cut one edge and then it's a path. Yeah. So but for this case, because we have a different, so we can't have the same graph for both HC and HP because they are not identical. So if for graph G, we have a Hamiltonian cycle, and then what we need to do is to cut this one and point this to V prime, because this is a neighbor of V, so it will also be a neighbor of V prime. And then we connect, this is connect to U prime, connect to V, U. Okay, and this is a Hamiltonian graph for G prime. And we successfully proved this direction. Let's see the opposite. So if G prime has a Hamiltonian path, then we can construct a Hamiltonian cycle in G. So first of all, because U and U prime has only one edge, so they should be the start. Yeah, but this because we're talking about graph G having a Hamiltonian path, but only graph G prime, but only graph G has a Hamiltonian cycle. So if you connect like U to U prime, then it's you have extra vertices which is not in G. So, but anyway, so U and U prime must be the start and the end because it only has one edge. And if you want to include every vertex, and they should be included, so they should be the start and the end. And so you have a U to U, a U to V to something, and then to V prime to U prime. And then what you need to do is to delete this one and also delete this part and connect to here. And this is a Hamiltonian cycle for graph G. Yeah. No, we have G prime is we don't delete V, we don't delete V prime. So I will say the construction one more time. We have a graph G here, and so this is graph G, and we randomly select a vertex here, V, and we duplicate this vertex, which means we will connect V prime to all the neighbors of V2. And we'll also create two more vertices, U and U prime, and connect U to V, connect U prime to V. And this new graph is G prime. Yeah. Okay. Yeah, so we successfully reduced HC to a HP problem. So this reduction means if you have a problem of HC, we can yeah, because for we have yes, no, and we also have yes, no for this is HC, this is HP. Yeah, so you have many ways to prove this, the relationship. So you can prove that this way, and or you can also prove this way. Let me see, this way, yeah, or like this way. So you have many ways, but you have to prove, yeah, to complete this part. Okay, so do you have any more questions? If you don't have any more questions, let's go to next. We'll do the opposite direction. We want to reduce HP to HC. And this is easier. So if you have a graph G for HP, and then what you need to do is to create one more vertex here and connect this vertex to all the vertices inside G. And this new graph G prime is for the HC. And so, and now we have to prove that if G has a HP, then G prime, G has a HP is equivalent if and only if G prime has HC. So first, let's see this direction. If G has HP, then it has a start point and an end point. And we just need to connect them to this new vertex. And then it forms a cycle, a Hamiltonian cycle in G prime. And it's done. And let's see the other direction. If we have a cycle here in G prime, then we just need to delete this one. And then it's a path in G prime. It's a Hamiltonian path in G prime. So this is pretty easy. And do you have any questions? Okay. So next, let's see a new one. We want to reduce HP to HP2. HP2 here means we specify the two vertices as the start and the end. So, for example, if you have to give a graph G to this HP problem for it to determine whether graph G has a Hamiltonian path or not. But but for HP2, you have to keep G and also two vertices for it to determine that whether G has a Hamiltonian path between X and Y, starting from X and ending from Y, ending at Y. Okay, so how can we reduce this? Again, we have a graph G for this HP problem. Then we will create two vertices A and B here. And we will connect A to every vertex in G, and also B to every vertex in G. Okay, so again, we have to prove the relationship. So if graph G has a Hamiltonian path, then we want to know that whether we can reduce it to a problem of G prime having a Hamiltonian path with two vertices. And we can, so if under this construction, we will give AB as the starting point and the end point for this HP2 problem. And if G has a Hamiltonian path, so you start from the U and end at B, then because A and B are connecting to every vertex in G, you can add A here and B here. So, and this is exactly what we want. So this satisfies that G prime has a Hamiltonian path between A and B. And for the opposite direction, if HP2 has such a Hamiltonian path between A and B, then we just need to delete them to get the HP for this G. So we complete the proof. Do you have any questions? And if you don't have any questions, let's move on. Next is about vertex cover. Let's first review the concept of this vertex cover. You are given a graph G and a positive integer K, and you want to know whether there's a vertex cover of size at most K in G, which means you have a vertex set and the size is smaller than or equal to K. And for every edge in the graph, at least one of its endpoints is included in this set. Right. And so here we want to reduce VC vertex cover problem to a VC 1/3 problem. This VC 1/3 problem is that whether you can find a vertex cover with at most 1/3 of the number of vertices in this graph. So it's equivalent to a VC problem. So you have a VC, and the K is set to V/3. Yeah, it's related to the number of vertices. No, VC is not a spanning tree. Not necessarily a spanning tree. Yeah, because you can have this example. So you can have this too. And so this has two cases. For this VC problem, so suppose you have a graph K. You have a graph G and you have a number K. You want to know whether there's a vertex cover of at most size K. And then if 3K is smaller than, is greater than or equal to V, then we will do this. So let's see an example here. K is equal to A and V is equal to 20. And so if we add such a graph, this is the star graph of 7 vertices. And then we will have 27 vertices, 20 plus 7. And for this graph, we need at least one node here in the vertex cover set. And so so there can be at most 8 for this one if we have K is equal to 9, because we have 1 for here, and then this can have up to 8. And then if you see this number, it's exactly what we want, because K is exactly V/3. So we will construct the graph like this. And this is for the case that 3K is greater than or equal to the number of vertices in the graph. And the basic idea is to construct, is to make the number of vertices in the new graph to be 3 times large, extra component. So if you are considering adding such a star graph, then, and what we want to do is to make, because we have K and V here, and we want them to be in this relationship. And then if they have this relationship, then we can directly put it into this problem, but it's not. So we want to add this graph. And so suppose the number of vertices in this star graph is T, then we need to have one more vertex in the vertex cover set. And this will have T more vertex. And if you solve this, it will give you, I think, this number, T is equal to this, which means you have to have a star graph of this size, of size T. And then you are guaranteed to construct a new graph G prime. And they are identical, and this is a successful reduce from VC to VC/3. Okay, so another case is if 3K is smaller than V, then we will add this. So this is S2. It's also a star graph and we will add many star graph here to make it, again, make it number of vertices in the vertex cover set is 1/3 of the number of total vertices. And the calculation is here because you have K and you have V, and you want to make it this 3. So if you add such if you want to know the number of such graph added to this G, suppose it's T, then for each T you have to have one more vertex in the vertex cover set. And for this graph, you will have two. For each of this graph, you will have 2 more vertices. Oh, okay, yeah. Then you, oh, okay, Professor Tsai talk this in class, then I don't think I need to go to detail. And this is how you compute the number of such graph you need to add to this graph to make it a problem of VC1/3. Yeah, so, but yeah, the main idea. Okay, yeah. So, it just talks, yeah. So I'm talking about the other direction. Yeah. And so, and this is how you compute the number of such graph added to the graph, to this G prime. Okay, and do you have any questions about this? It looks a bit complicated, and I want to remind you that the purpose of reduction is to reduce a problem to another problem. So originally, you have a vertex cover problem of size k, but you suppose you know how to solve this problem. You want to reduce this problem, this VC to VC1/3. But because this VC1/3 problem can only solve a problem that k is exactly V/3. So we need to construct a graph, a new graph. So if we have a graph to solve for VC, we have to construct a new graph G prime, such that if VC1/3 is yes, meaning it has a vertex cover of at most V/3 vertices, then we can construct a graph in G having a vertex cover set of at most size k. And this is our purpose. And the reason we have to construct a new graph is that otherwise we can't meet this standard. So yeah, this is a mapping between them. And for this problem, what we need to do is to make the number of vertices in the vertex cover set, the maximum number to be 1/3 of the number of vertices in the graph. If you don't have any more questions, we can go to the next problem. It's another new. So we want to reduce VC to VCH. VCH is it's also a vertex cover problem, but it has some restriction on the vertex cover set. So if you have a vertex cover set V prime and then of size k, then the induced graph G must be Hamiltonian. So which means it has a Hamiltonian path in this induced graph. So how can we reduce VC to VCH? If we have a graph G here for VC problem, then we will add, and we also have a K, right? So suppose K is equal to 4, meaning that we want to find a vertex cover set of at most size k, size 4. And then we will add 2k vertices here. And k of them will be, so they are paired and they have connections in each pair. And then k of them will be connecting to all the vertices in G. Yeah, and this is our construction, and this new graph is G prime. And what we need to do is to prove that, again, to prove that if graph G has a vertex cover set smaller than or equal to k, then G prime will have a VC of size k, of size 2k. Because under this construction, we will set the number of, set this k in this VCK to 2k. And it's Hamiltonian. It has a HP. So let's see this direction. If you have a vertex cover set of k, then for this graph we can find the, so you can choose these vertices to be included in the vertex cover set, and then you can have a Hamiltonian path because these vertices are connecting to every vertex in G. So you can just go, and the number here is exactly the same as number in the vertex cover set inside. So you just need to go like this. And you complete. And for the opposite direction, if you have a graph G prime and it has a VC of size 2k, and it also has a Hamiltonian path. So first of all, because we have this edge here, this means at least one of these two vertices is included in the vertex cover set. And so, but if you have this one in the vertex cover set, in order for the induced graph to be Hamiltonian, then you must have this one as well, because you have to have a path, and this is the only edge. And so you have to have this as well. But if you have this one, then this one is no longer needed. So the first result is that this k vertices will always be in the vertex cover set, will always be in VC. And then, so this means if we have a VC of size 2k, then we will definitely have a VC for this set of size k. This means we can find at less than or equal to k number of vertices in graph G to form a vertex cover set. And we're done. I think, yeah, we're done, because we just need the property of vertex cover. We don't need this one. Yeah, for this VC problem. So you exclude all the vertex here in the VC for this VCH. Then you get a vertex cover set for this VC problem, and that's what we want. So is it clear? It smaller than it doesn't really matter, because the problem of vertex cover set is that you're supposed to find a vertex cover of size at most k to be smaller than or equal to k, because as I said, if you, for this graph G prime, and if you have a vertex cover set and the induced graph of this set has a Hamiltonian path, then these four, not four, but this K vertices must be included. So this is my first claim, because for this edge, for each of this edge, you must have one of its endpoints. And if you have this one, and in order for it to be Hamiltonian, you still have to have this one in order to connect them to be a path, right? Otherwise, it's isolated. So, but if you already have this one is not necessary. You can have it or you cannot. You may or may not have it. So my conclusion is that this K vertices will be included. Do you mean from this G to, do you mean converting a yes instance from G to G prime? You mean this one? Oh, no. For this G, we don't require it to be Hamiltonian. Yeah, because for VC problem, if you are talking about G, then I think you are talking about the VC problem. We don't require it to be Hamiltonian. And then, yeah. So since we have K here, then the number of vertices here will be definitely smaller than K or equal to K. Okay, do you have any other questions? If not, we can go to our last part of today. And it's much easier than previous discussion. Let's review two concepts of two problems. One is partition and one is subset summed. No, no. If VC is equal to K, or independent. I don't know what you mean by independent. If VC is equal to K, they can't be independent. Oh yeah, they can be independent. But so we don't really consider this problem in a VC problem to be independent or not, I think. Because if you have such a graph, then in order to cover all three edges, you can't select a vertex that is independent, right? Because if you select one, then you can only cover two edges, and then you have one left. You have to select either one here. Anyway. No, K is the number of vertex. It's the size of the vertex cover set. So for example, in this case, if I select these two, and so I have a set of two vertex here. So this is, we have a size 2. And K is required for your vertex cover set to be smaller than or equal to it. And yeah. So our last problem is about partition and subset sum. For partition problem, you're given a multi-set S of integers, and you want to know, this is S, you want to know whether you can partition it into two sets. This is S. One is S prime, one is S minus S prime, and the sum of both sets are equal here. And for subset sum problem, it's pretty similar. You have a set S and also an integer T. And what we want to know is that whether you can have a subset S prime that has and the sum of this subset S prime is T. So yeah, this is the definition of these two problems. And let's see how to reduce from partition to subset sum. For partition, you have S, and so it's pretty easy to reduce it to subset sum because you have the exactly same S, and you set the T, the targeted subset, target sum of the subset to be half of the sum of S. So it's pretty straightforward. If you can partition S into two parts with equal sum, then you should be able to find a subset with half of the sum of S, right? And this is identical because the other part will automatically be again this sum, which means the solution is the same. So we prove both direction. If it's a yes instance for this partition, it's also for subset sum and vice versa. Okay, and let's see how we can reduce subset sum to partition. So we have a set S, and also a number T. And for this subset sum problem, we want to know can we have a subset of S whose sum is T. So we will add one more element of this value to the set S. And this larger set, let's call it A, is for the partition. And then we need to prove again. So let's say if this instance is yes, if we can find a subset sub S prime that has sum of T, we can always find a partition for this new set A for partition, because you have S here and the sum of it is T, so the other part is S minus T, and the value of this element is this one. So if you put this into here, then I think what you get is T, right? Because this one is equal to this, and you have 2T here, you minus 1T here. So the sum of this part will be also T, and the sum of this part is also T. So we create so the partition problem can be solved. It has a partition, a legal partition. And on the opposite side, if we have a legal solution for this partition problem in the set A, then so it's a partition problem. So you have two sets, and they have the same the same amount of sum. And because you know that the sum of S is sum S, and you also have one more element in A, and if you sum them, then it's 2T. So the partitioned two sets is both have sum of T, and you just need to use the one without this element, this created element. Let's say it's here. Let's say it's here. Then you just need to use this one in the original set of S as the subset for this subset sum problem, and you get the target. you have a subset of some t. Okay. So is it clear? Do you have any questions? And this is the end of today's tutorial. If you have any questions, you can ask. Otherwise, you can leave.